All right. Okay. So we only got a couple more weeks. There will only be this PowerPoint and one more after this. Uh, I think this one will probably be about an hour and a half. And for the 121 class, maybe a little bit shorter for the 110 class. Okay. All right. Well, so up to this point, what we did is we had the electronic structure of the atoms. And from that, really what we're interested in, uh, one thing is to figure out, if you know the structure, you figure out the function. Okay, and a couple of functions that we figured out were based on the size of an atom, which is related to its electronegativity, and the valence electrons, which will relate to the reactivity of an element. The column that the element uh, is related to its chemical properties, which is also related to its number of valence shell. The row that an element is in is related to its energy level, or how big it is, and its valence shell. We ended the last PowerPoint talking about ions and why ions have the charges. When it comes down to it, most ions will have, the common ions will have the same amount of electrons as the nearest noble gas. Remember, that doesn't mean they turn into noble gases, it just means they have the same number of electrons. That can be stated as the Octet Rule or to achieving noble gas status. Now, neither of them are really what goes on. Remember, this is that when an atom gets its most common charge, it has to do with energy, not wanting to become like a noble gas. Now, becoming a noble gas is just a secondary effect. Well, it does become a noble gas. It has the same electronic configuration as a noble gas. Okay, and that's just an outcome of the stability of an atom. Now, there might be more to it, but what we have is this is how we define it. But just like a lot of things we do in chemistry, we just want to have a quick way of coming up with the answer, and we'll say is that the atoms will have the octet rule or achieve noble gas status. Right. Okay. So we'll be using a little bit of that for what we're going to be talking now, and we'll be exploring covalent molecules, how they're. All right. So let's first look at forming ionic compounds. Forming ionic compounds seems like a pretty simple thing. You just get a plus. You get a positive electrical ion, like sodium plus, Na plus, and you get a negatively charged ion, like Cl minus, and you just bring them close together. They attract each other, and you got your bond. Okay, and that's called an ionic bond. All right, and it's that simple. Now, one of the things I want to make clear is that a lot of times in chemistry, people get things mixed up. Bonds, when we talk about bonds, it's what holds together the atoms inside a molecule. Remember, molecules are made out of atoms, and the atoms are connected chemically, and for ionic bonds, the way that they're connected is through ionic bonds. So let's look at covalence. Well, covalence molecules. What's happening here? How do these atoms stick together like water? How do the two hydrogens of water stick to the oxygen of water? All right. Well, remember, covalent compounds are made out of nonmetals, and that's a big deal. Kind of think about. Think about what nonmetals from last PowerPoint. Nonmetals have high electronegativity. They usually want to have, if they're going to have a charge, it'll be negative. They don't like to lose charge because the electrons are close to the protons. Okay. Well, unlike ionic compounds, spelling error, there's no positive or negative charges. So there's no inherent attraction between the atoms. So in water, there's a dual hydrogen oxygens, and they're not naturally attracted to each other like plus and minuses. There's something else that's going on. Again, nonmetals have high electronegativity, so they won't become charges. So they can become a charge, but if you have two nonmetals and both of them want to become negative charge, and if they both can become negatively charged, they would repel each other. Okay, so it has nothing. It hasn't to do with gain or lose electrons. It has something else. And well, it's a little bit more complicated than just getting attracted together, though that's going to have a little bit of an effect. I am just going to basically touch on why this bond forms. Then we're going to we're going to spend most of the time on how they form their particular structures. Okay, why do covalent molecules form? All right, so going back to ionic compounds, why do ionic compounds form as well? It has to do with the reduction of potential energy. When you have a plus charge, it would really like to have that plus charge balance out with a negative charge. So it's because it's not naturally good to have a plus charge, okay? Unless, that's the way we're going to look at it. There's always ways that you can make them stable. But one way you can make plus charge and a minus charge stable is combine it with its opposite charge, and they come together. So the key thing is you reduce potential energy, becoming more stable. Well, covalent compounds, there's no attraction charge, but there's still a decrease in potential energy and an increase in stability. And the reasons for that are two. One has to do with sharing of electron density in the valence shell. Now this really involves more quantum mechanics of looking at waves and how waves interact with each other, and we're not going to go into that. It's very interesting as usual, but for brevity, we're going to skip that. But just remember, it has to do with sharing electrons between valence shells. Okay. Another reason why it lowers the potential energy is the valence electrons, when they do bond, when they do come in contact with another atom, the protons and electrons get closer, and again, that's going to make the electrons more stable. And again, this would be studied in a higher level chemistry class. So there's two things going on here. One, you have the sharing of the electron density, and the other one is the increase of the attraction between the protons and electrons. These produce attraction between atoms in the covalent molecules, and we call these covalent bonds. And that's all we're going to say about it. All right. So now we're going to look at how do they form. How does water form its particular bonding structure and three-dimensional structure? Well, we're going to go try to figure this out, the structure of the covalent molecules. First thing we're going to do is find the bonding structure. How are the atoms, what is the connectivity between the atoms? And then in the next PowerPoint, we'll talk about the three-dimensional aspect of these molecules, because that's really the key. Molecules are three-dimensional, and their three-dimensionality really determines how they function. And also we'll be looking at how they share electrons or polarity. These last two will be covered in the next PowerPoint that will go out next week. Okay, so what we want to do is determine the bonding structure. And so what is the connectivity relationship between atoms and a covalent molecule? And we're going to start out with water, H2O. One of the things you have to do when you do these, you always have to be given the molecular formula. I used to think you didn't have to know that. You could just take any 2 or 3 atoms and say a chemical formula, and you could come up with the structure. That's not the case. Okay, so you have to be given a real chemical formula. Okay, then what you do, you draw the Lewis dot structure of the atoms, in this case 3 atoms, into a skeletal structure with the lone atom in the middle, oxygen. Okay, so you put oxygen in the middle, and here's the Lewis dot structures. Okay, so you have, if you go back and look at, this is what you had to know for this test coming up, or test 4, is here's the Lewis dot structure for hydrogen, here's it for oxygen, here's another. So hydrogen has 1 electron in its outer shell and 1 hole. Oxygen has 6 electrons in the outer shell and 2 holes. And here's the other one. And one next thing we need to do after we draw the skeletal structure, which is H, put the oxygen in the middle and the hydrogen on the outside. And we're going to end up looking more closely at center atoms down the road. But right now, if you're given a structure and there's only 1 atom of it, you put that 1 atom in the middle and then surround it. Okay. Symmetry is always a pretty thing in science. Okay. So sometimes when I've had students, they'll do OHH or something like that, or HHO. Symmetry, one way to keep about it is that things sort of fit around each other, and there's actually a reason for all that. Okay, so we have our center. We have our skeletal structure with our 3 atoms. Next thing you do is you count the number of dots. Okay. All right, the number of dots, which are the number of valence electrons, equals 8. 1, 2, 3, 4, 5, 6, 7, 8. And keep that. Keep that to what we want to do is when we're all done, the same number of dots have to be there. All right, after that, what you do is you have the dots fill the holes. Okay, so here goes here, there goes here, here goes here, here goes here. And so now there's a dot inside this whole dot, inside a dot. Okay, so what you have now is you have a shared electrons here. So these 2 electrons essentially belong to this hydrogen and this oxygen. So hydrogen now has 2 electrons in its outer shell, and oxygen has 8. Okay, so the green and the holes. All right, so we do is we count the number of dots, and we saw that it was 8. Okay, well, let's look at it a little bit more closely. Each atom again. If we look at each atom, let's notice is that so I'm just looking at the hydrogen. It had these 2 holes filled, so it has a full valence shell. Remember, hydrogen is in the first shell, and the first shell could only have 2 electrons. Same thing here. Now oxygen has 2 of its own electrons, and now it's sharing 4 from 2 hydrogens, but in a sense oxygen also can claim these electrons as its own, even though they are here and here. So oxygen now has 8 electrons in the outer shell, which is how many electrons you can put in the valence shell, the valence shell of the second shell. Okay. All right, this means there are no more empty spots in the valence shell. It has the same, now oxygen has the same number of valence shells as neon, okay, the nearest noble gas. And hydrogen has the same number of valence electrons as its nearest noble gas, helium. So after we bond, typically, and we're going to see that for 121, this will not always be the case, is that you will have valence shell filled, which is achieving the noble gas status, we say, even though that may not really be the case. It does not achieve anything. It's just that that's the end case. And it has the octet rule, except for hydrogen, which only could have 2 electrons anyway. So as we go through these, for the most part, you'll see that you'll have 8 electrons in the outer shell for most atoms, except for hydrogen. Keep that in mind. Okay. Now, this is specifically for the 121 class. And we'll see that there's exceptions to the octet rule and why this is. We'll see that there are different exceptions to these outcomes, but for now we're going to use these checks, the achieving noble gas and the octet rule. But let's take a look at why there might be exceptions to the octet rule, and we'll see that down the road. Okay, so let's look at the orbital energy diagram for the first 2 rows elements. So that's this. So 2 row elements would all be here. They have their first energy level filled, and then depending on who you are, you're somewhere in here. Okay, so let's say you're nitrogen. You'd have 7 total electrons. 1, 2, 3, 4, 5, 6, 7. So you would have 3 spots left over. All right. All right. So the second energy level is their valence shell, and the total amount of ballots available are 8. So as many as you can put in here are 8. So nitrogen could add 3 more electrons, but it can't add another one. All right. Well, you could, but it'd be really hard. All right. You have to add a whole new energy level. But for stability purposes, you really don't want to add new shell. Okay. So if you're in the second row, all the second row elements can have no more than 8 electrons. It just can't. Okay, at least in terms of stability. Okay. Right, and now also remember that we were talking about the orbital energy diagram. We said that the most electrons you could put in a valence shell were always 8. Okay, and that's because of the way you fill them up. Okay, you got up, down, and so forth. And using our model, we never got more than 8 electrons in our shell. Okay. However, filling the OED of an atom as a singular entity, not bonded to something else, is an exception, an exception, because atoms can connect with other atoms to form molecules. So what I'm saying is that the OED only looks at the atom when it's not bonded. And it turns out that when an atom bonds, it has a kind of different rules than the orbital energy diagram. And what can happen, so let's take a look at element, and for row 2, as far as you can go, is you can only put 8 electrons in the outer shell. But let's say in row 3. Okay, so row 3, you could put 1, 2, 3, 4, 5, 6, 7, 8, usually, okay? But if it comes down, if there's something that somehow causes the outside energy to expand, it can expand because it's got a d subshell. So 3, energy level 3, it can have up to 18 valence electrons. You won't see that happen a lot, but it's possible. In fact, the element palladium, okay, its OED does have 18 electrons in the outer shell, okay? And that breaks the octet rule. All right, okay. So the first few models that we're going to show of covalent molecules will follow the octet rule. But we're going to see at the end of this lecture that we'll get into exceptions. And we just got to accept them, especially if they're in the 3rd, 4th, 5th rows, okay? If they're in the second row, you go out and have 8 valence electrons. Okay, so what we're going to do now is continue talking about water. So we had the Lewis dot structure, or the holes filled up. So the bonds, or where both atoms can claim that they own them. Okay, now what I like to do is I like to replace the shared electrons with a dash. That way it kind of looks like a bond, okay? And I call that a bonding structure. And like I said, I prefer this in the long run. Don't leave these extra dots that were found that are not bonds, because they are really important and they're called lone pairs. So what we want to be able to do is we want to be able to draw the bonding structure of a molecule. Okay, so let's do ammonia now. So first thing is you draw the Lewis dot structure of each element, and into a skeletal structure, put the lone atom, nitrogen, in the middle, and put the dots, okay, in the holes. Right, and then what you do is you count up the number of dots. 1, 2, 3, 4, 5, 6, 7, 8. All right, and then what you do is you fill the holes. Okay, this guy goes here, this guy goes here, this guy goes here, this guy goes here, this guy goes here. And then what you end up with is over here. Now, just want to let you know that I could have matched, I could have had this hydrogen up here at the top and these here at the top. It doesn't matter where I put these H's. I could have had HHH, okay, HHH, HHH, okay, but there'll always be one set of pair of electrons that are not involved bonding for nitrogen. Okay, after we fill in the holes, what we have is we have shared pair, and each shared pair, each atom can claim that pair. So nitrogen now has 1, 2, 3, 4, 5, 6, 7, 8 electrons in its outer shell. Each hydrogen has 2, so each one of them achieves noble gas status. Okay, and what we can do now is we can replace these with dashes. But again, let's just go over this. So nitrogen now has 8, 2, 2, and 2, and so forth. And what we're going to do is replace the filling and filled holes with dashes, and you get something like this. Okay, where nitrogen has 3 bonds and 1 lone pair. Okay, so what you're going to do when you do this, you do, first of all, you get a formula. You draw the Lewis dot structures, count dots, fill the holes, okay, and then you count the dots, and the dots should equal the dots that you start out with. So here's my thing. So the first thing do is draw the Lewis dot structures. Count the dots, 1, 2, 3, 4, 5, 6, 7, 8, and fill the holes. Okay, and you get this. So now again, each atom can claim that it has a pair of electrons. Oxygen can say it has 4 pair, and each hydrogen can say it has 1 pair. So carbon has a full valence shell, has 8 electrons in its outer shell, and hydrogen has a full valence shell. I'll count up the number of dots, 1, 2, 3, 4, 5, 6, 7, 8, and that's what we set up here. So check it off and replace these shared pairs with dashes, and here you go. All right, carbon dioxide. Now this is going to be a little bit, you got to keep an eye on this. It just gets a little bit more complicated, but not really if you just follow. The key is to fill holes. All right, so you start with your Lewis dot structure, put carbon in the middle, lone atom, and then you count the dots. We got 6 here, we got 4 here, that's 10, and then we got 6, so we have a total of 16. All right, so notice the other ones we had before had 8. Okay, so 8 is not a magic number when you count these dots. Depends on the molecules. Right. So what you do is you fill the holes. So So you line these guys up so you can fill these guys and these guys. That makes sense. But now it gets a little bit messier. But that's okay. What you do is you try to deck these two will share over here, and these share over here. And you might get some crossing and all that. And it looks messy, but we'll clean it up in a minute. So here's what we get out of it. Notice that there is a lot of crossing over. You really just want one pair to meet up with another pair. Okay, and you can see that this should be carbon, has two sets of connections to each oxygen. So carbon connects here and it connects here, so it has two bonds. And it connects here and here, so it has two more bonds. Okay, so it's going to work here. So it has here's a bond and here's a bond. So it's this one and this one. And it has this bond and this bond, which is here and here. So we just cleaned it up. Okay. And when you do that, you count your dots. 2, 4, 6, 8, 10, 12, 14, 16. Voila. Okay. The carbon still has two sets of connections. Okay. Each carbon has two sets of connections to each oxygen. 1, 2, 1, 2. And there's lone pairs on each oxygen, two sets of lone pairs. And it doesn't matter how you put the lone pairs. You can put them like here and here, or here and here. You know, so I just have them here and here. It doesn't matter. They could be opposite of each other. They could be right next to each other. Okay, just have them separate from each other. All right, now what we're going to do is we're going to replace these shared pairs with dashes, and we get our bonding structure, which is this. This up here shows the claimed electrons. Oxygen now can claim, this left oxygen can claim its own 4 over here, and plus the 2, plus the 4 that's sharing, so it now has 8 in its outer shell. The carbon now has 8 electrons that it can claim, and the oxygen claims. So notice is that these electrons are not belong to just oxygen, but they also belong to carbon. But oxygen says it can claim them, and carbon can claim them. All right. Okay, replace the shared pairs with dashes, and you get your bonding structure. All right, now let's look at formaldehyde. You don't have to know the name, but let's give you the formula. You should be able to figure out the bonding structure. So again, you start off with the Lewis dot structures of each. Now you have a choice. You have a choice to put, so you have two lone atoms here. You have carbon and oxygen. Which one do you put in the middle? Well, technically, it usually works like this. Well, first of all, if you have hydrogens will always go on the outside. They'll never be in the middle. That's because they could have only one bond. If you put hydrogen in the middle, that means it could have 2 bonds. Okay. All right, so that goes on the outside. Now, you have a choice between carbon and hydrogen. So why do we put carbon in the center atom? Well, technically it has to do with electronegativity. Usually, the center atom will have the lowest electronegativity, and we'll get into that more when we talk about for 121. But so carbon has a lower electronegativity than oxygen. You can look at the periodic table. Hydrogen is further to the right than carbon, so that tells you it has a higher electronegativity. So we're going to put carbon in the middle. And then we'll count up the dots. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay. And then what we're going to do is we're going to fill the holes. Okay, that's easy. And that's easy. And that's easy. But you got an extra pair over here on carbon, extra pair up here, so move them up here. Now notice, just like in the last one, carbon has 2 connections to oxygen. All right, so after we fill in the holes and clean it up, we get this structure. Okay, where each carbon has one bond to hydrogen and two connections, two bonds to oxygen. Count the number of dots: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And that's how much we started for. And replace the shared pairs with dashes, and you get this structure here. And it doesn't matter where you put the lone pairs. You can put them here, here, okay? I just left them the way they are. Okay, HCN, known as cyanic acid. Again, draw Lewis dot structures. HCN, okay, carbon goes in the middle because it has a lower electronegativity. And usually, if you get carbon, usually carbon will go in the middle if it's given a choice, but use the electronegativity as a way to figure it out. So carbon goes in the middle, nitrogen, hydrogen. And then you fill the dots, okay? And notice my dots kind of crisscross here. Doesn't matter, just fill in the holes. Say fill that one and fill that one. Then it gets a little messy. This has to fill over here and this has to fill in here. But notice that carbon has three connections to nitrogen. 1, 2, 3. So that's going to be 1, 2, 3. Okay. And one hydrogen. And there's still a lone pair. So what you do is you replace each one of these with a dash. I know they're kind of set up different. These kind of go up and down. These go sideways. But I hope you can see that. So this is shared pair. This is shared pair. And so that's way across. Then you count the dots, get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, which is what we want. Replace the shared pairs, this with dashes, and you have this as a bonding structure. So you have single bond, carbon, hydrogen, and a triple bond, it's called, between a carbon and nitrogen. For carbon dioxide, we had 2 double bonds. Here we have a triple bond. That's as high as you can go. You can have a single, double, or triple bond. All right, hydrofluoric acid. Okay, same thing. Started out with the skeletal structures. In a sense, there's no center atom, so you just put them between each other. Count up the dots: 1, 2, 3, 4, 5, 6, 7, 8. Fill the holes. Ding, ding. Here you go. Count the dots. You got 8. And replace the shared pair with the dash, and you got this structure here. Okay, hopefully it's pretty simple. So what I'm going to do for both my classes, 110 and 121, I'm going to send you out a list of chemical formulas, and you have to figure out their their structural bonding structures. Okay, so we'll continue with that, but these are the general ideas. Now, what I'm going to do now is go over a little bit different, some more things. There's other ways you can maybe find out bonding, and we're going to look into that. So if we went back and we looked at all the structures we just came up with, if I could set up a table, I get a table like this, where if I look at the elements, the number of holes, bonds, lone pairs, what that element is, the periodic table, and then see what kind of bonding structures I've had, and I have bonding arrangements. So let's look at carbon. So carbon had 4 holes, and it had 4 bonds. Because for every hole there would be 1 bond. Carbon didn't have any lone pairs. It's in the 14th column. So if you go back and look, you'll see that we had these 4 different cases of carbon. Carbon have 4 single bonds. As in methane, it can have 2 single bonds and a double bond, like in formaldehyde. It can have 2 double bonds, in like carbon dioxide. And it can also have a single bond and a triple bond, like cyanic acid. Okay, it can't have anything else. These are the only 4 ways that carbon can connect. So that carbon has 4 bonding arrangements. All right, now the other thing about it is that because all the elements in a column have the same Lewis dot structure, anything in carbon's column is going to have the same amount of bonding arrangements. For instance, if you had silicon, silicon can have, it's right under carbon in the periodic table. That means it has 4 holes and 4 bonds. It can have 4 bonds. So it can have these 4 different arrangements. Right, nitrogen. It had 3 holes in the Lewis dot structure. That means it can have 3 bonds, and it has 1 lone pair. And it's in the 13th column. So nitrogen, everything under it will have the same number of, 3 holes, 3 bonds, and 1 lone pair. And if we look back to the structure, we saw 2 of these. It had, ammonia had 3 bonds, 1 lone pair, 3 single bonds. And then we just saw one with cyanic acid, which had a triple bond. There's another case we didn't see, but there's another way that nitrogen can bond with 1 bond and 1 single bond and 1 double bond. So nitrogen has 3 bonding arrangements. All right, now let's look at oxygen. So oxygen, if you go back, it has 2 holes. That means 2 bonds, 2 lone pairs, and it's in a 12th. So everything in its column could have the same number of bonds, lone pairs. If you go back and look, there were 2 ways that oxygen can bond. There's one's like in carbon dioxide and formaldehyde. It had a double bonded oxygen. And like in water, it had 2 single bonds. So the number of bonding arrangements is 2. And then the last one we saw is fluorine. Fluorine has 1 hole, 3 lone pairs. It can have 1 bond. It's in the sorry, these should be changed. This should be 15, 16, and 17 in terms of the columns. All right, and fluorine. So fluorine can have 1 bond and 3 lone pairs, and anything under it, like chlorine, bromine, iodine, is going to all look the same. And hydrogen, it looks quite a bit like fluorine, but it doesn't have lone pairs. It just has 1 bond, and could have only 1 arrangement. So if you look, it's kind of cool. Is that the number of bonds an element can have is related to its bonding arrangements. So carbon has 4 bonds. Guess what? It's 4 bonding arrangements. And so forth. So we're going to use these bonding arrangements instead of connecting dots. And I kind of think if it's a little simpler once you've really figured it out. All right, so each of these elements will have a corresponding number of bonds, lone pairs. Okay. And I just went over this about kind of the columns. And then each atom has different amount of bonding arrangements, and the number of arrangements is equal to the number of bonds. Okay. So what we're going to do is figure out the bonding structure a different way than just filling holes. And we're going to use the above table and the bonding arrangements. So let's look at water. Again, we need to start out the same way. So start out with your, so you don't need to put any dots. Just put the HOH as your skeletal structure. Instead of counting the dots, add up the valence electrons. So hydrogen has 1 valence electrons, oxygen 6, and have 1. So it's actually equal to the number of dots. But so we're not going to put the dots in here. And then what you do is you're going to start with the outside atom. So what we're going to do is we're going to go to the table and just look at, and we're going to find hydrogen and give it how many bonds and lone pairs it has, and then we're going to put that here. And we got that. Okay. All right. So we're not done, maybe. Okay, so, all right. So we just did that. So you start with the outside atoms first. Right, now what we want to do is take care of the oxygen, make sure it's right. Okay, so we're given two choices. Okay, remember oxygen has two bonding arrangements, has a double bonded and two single bonds. And if you notice, this case here looks like the one we just had at HOH, the previous one. And so what we need to do is just add the two dots on top and bottom, and we're done with our structure. Okay, so now each hydrogen has one bond, and oxygen has two bonds, two lone pairs, just like we said from the table we just put up. Now if you count up the number of dots where dash is equal to, it should equal the number of total valence electrons. 2, 4, 6, 8 equals the number of valence electrons. Voila. And if you go back and look at the other water molecule, it's the same. Right, now let's do carbon dioxide. Again, count the number of valence electrons. So oxygen has 6, 4, and 6 equals 16. Here's skeletal structure without dots. Again, you're going to start out with the outside atom, go to the table, look for the oxygen, which one of the oxygen is the best. So this oxygen is only connected to one thing, so you're going to pick out the oxygen that's only connected to one thing. So this oxygen will connect only to one thing. Okay. If you pick this one, it would have to connect to another thing over here. So you're going to pick that guy. So there'll be a double bond here. So it has one connection, a double bond. And then it's the same thing over here. It's one connection and a double bond. So you write it out like this. Okay, so you got your outside atoms. So always get your outside atoms. Now we want to see if we need to fix the carbons. Okay, so so we have a carbon here with two double bonds. Well, if we go up and look at our table, we can see that, aha, here we go. This guy here is the same as this, so we don't need to add anything. We should be done. Okay. In the previous water, you had a structure, had two dashes and two dots, so you had to add the two dots to make it look like the right oxygen. This one you don't. It's all set. So now everything's exactly like it should. Here's the oxygen. Here's carbon, and here's the oxygen. Okay. Right, let's count it up and see if it works. Each dash is 2, so 2, 4, 6, 8, 10, 12, 14, 16. Bingo. Okay, now here's another variation on this method. Okay, so, and all it's going to do is really concerned with the outside atoms. All right. So we're really not going to be concerned with the middle atoms at all when coming up this structure. It's kind of cool how it works out. So again, you start out with, you count up the dots in your skeletal structure. And then you give the outside atom just its number of bonds and lone pairs. So hydrogen has one bond. All right. Okay. Now, what you need to do is so you have the outsides right. So now let's get the center. So you count the number of dots. Okay, a dash is 2, 2, and 4. So there's 4 dots. Well, we need 8. So we need 4 more dots. Okay, so what we do is those extra dots that we need, we'll just simply put them on the center atom in pairs. You don't put them all together as 4. 1, 2, 3, 4. You split them up into 2 pairs. And look at, that's exactly what we got before. And we didn't even care about what oxygen looked like, okay? And it turned out it works, okay? So this is really kind of the quickest model, as you get the you get your skeletal structure and your valence electrons. Take care of the outer atoms. Okay, count the dots and dashes. If they're off, then you add the extra ones that you need into the middle. If you, a lot of times you're not off. You don't have to add any. Okay, like in this case. So we're going to do CO2 the same way. So you have 6 plus 4, 16 again. Here's skeletal structure. Now what we're going to do is going to take care of oxygen. Each oxygen. Well, oxygen can have 2 bonds and 2 lone pairs. Alright, and you want to pick the right one. So you want to pick the one that has 1 connection. So you're going to pick this guy. So you put this guy in there, put this guy in there. Okay. So don't even worry about carbon. So what you do is now you count up the number of dots. 1, 2, 3, 4, 2, 4, 6, 8, 10, 12, 14, 16. And look it. You're done. And that's what you got from before. So this method, you don't even have to worry about the center atom, okay? All you do is figure out the outside atoms, and there's a reason for this, the outside atoms, and anything you're missing, you just put it in, you fill it, and take care of it at the end. Okay, so let's try formaldehyde again. Count up the valence electrons, get yourself in the right skeletal structure, take care of the outside atoms first. So hydrogen always gets 1 bond. We're going to pick the oxygen. Oxygen's going to have 2 bonds, 2 lone pairs. And it's only connected to one thing, so we're going to have a double connection here. Double bond as their 1 connection. Alright, now what we're going to do is count up the dots. So we took care of the outside. Alright, count up the dots. 1, 2, 2, 4, 6, 8, 10, 12. There you go. They're done. We'll do another one. Again, let's look at HCN. Alright, count up the number of valence electrons. 1 for hydrogen, 4 for carbon, 5 for nitrogen. We're going to take care of hydrogen and nitrogen's bonds, and then count the number of dots. Anything we need to fix, put it on the carbon. Okay, so hydrogen gets 1 bond, and we're going to pick, so nitrogen has 3 different bonding arrangements, so we're going to pick the one that only has 1 connection, and that's the triple bond. We're going to put it there, triple bond, 1 lone pair. Alright, so we have the outsides taken care of. So now what we're going to do is count up the dots. 2, 4, 6, 8, 10. There you go. Okay, so putting this together, and this will be the last slide for 110, is that you're going to see this. So the number, so if we set up a table, the number of connections on a center atom and the lone pairs on the center. So we had 1, 2, 3, 4, 5, 6 different scenarios. We had the case of carbon dioxide and cyanic acid. Both had 2 connections to the center atom, and the center atoms had no lone pairs. Okay, we had another situation where you had 3 connections to the center atom. This is formaldehyde, and the center atom did not have any lone pairs. We had another situation where you have 4 bonds to lone pairs, like methane. Okay, and then we had a situation like ammonia, where you had 3 bonds and 1 lone pair. Look at this one and this one are similar. Okay, they have both 3 connections, but this guy's have some lone pairs. Okay, then we had another situation like water, where it had 2 bonds and 2 lone pairs, which looks like this up here, but up here didn't have the lone pairs and this did. And then finally we had just 1 bond. So if you look at, there's a symmetry from here to here. It goes 2, 2, 3, 4, 3, 2. So these 2 up here kind of look like these 2 down here, except these have lone pairs. And that's going to become we'll use that in the next thing when we talk about the actual three-dimensional structure of atoms. I'm going to give you a set of problems, like I said, problems of, that you do, and actually they'll be found in your lab book. Hopefully you'll have them, your lab book still, and you'll find you'll come up with the bonding structures of 18 structures from your lab book. This is 110, and I'll have similar one for 121, and you'll come up with the structure for 18 of them. All 18 of them will fit in this column, on this table. They will all have either two connections, no lone pairs, 3, 4, 3, 2. That's it. Those are the only kinds of connections that we see, at least in 110. And 121, we'll see that it gets a little bit more complicated. But this is the general way. It's pretty simple when it all comes down to it. Okay, from here on in, it'll be just 121, and okay. All right, so this is for 121. You guys are more advanced, so to speak, and so, and if you've had chemistry 110, at least for me, you would have covered what we just did. Now what we want to do is get a little bit more in depth into it. Right. I talked about the expansion of the Valence Shell, or the Octet Rule, and we're going to see that right now. Okay, so we're going to look at these two molecules, PCl5, phosphorus pentachloride, and sulfur dioxide. Okay, and we're going to use the last method I talked about, and that's you count the valence electrons, start out with the skeletal structure, take care of the outer atoms, count them, and then fix the middle if you need to. So, count the number of valence electrons. Phosphorus has 5. Okay, it's in the 15th column. Everything in the 15th column has 5 valence electrons. Each chlorine has 7 valence electrons. It's in the 17th column. So you have 5 times 7 plus 5 is 40. So when we all get done, we should have 40 dots. So we can draw the skeletal structure, and it doesn't matter how you drew it. I sort of drew it 2 different ways. Okay, it's like a pentagon. Okay, and it's kind of good to, symmetry, line them up kind of symmetrical. So I'm probably gonna be using this one right over here. I could use this, it really doesn't matter. All right, now what we do is we give chlorine its appropriate bonding arrangement. So chlorine is in the same column as fluorine. So if you look at that table that I gave you, fluorine always has 1 bond and 3 lone pairs. So we're going to give each chlorine 1 bond, 3 lone pairs. Okay. All right. And then what you do is you count the dots. 2, 4, 6, 8. And you do that 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. And you have 8 5 times, which equals 40. And you're done. That's it. Okay. Now, so this is the bonding structure of phosphorus pentachloride. Let's take a little closer look at it. Notice that each chlorine has 8 electrons, so it follows the octet rule. But now look at phosphorus. Phosphorus has 2, 4, 6, 8, 10 valence electrons. Okay, and like I said, that's okay. I said it's okay because phosphorus is found in the 3rd row, and therefore it can expand into the D subshells. Okay, SO2. Count the number of valence electrons. Sulfur is 6, and each oxygen is 6 also, so it's 6 plus 2 times 6, 18. Skeletal structure. And we're going to take care of oxygen first. All right, my cat's decided to talk to me. All right. So where was I? All right. So we can deal with oxygen first, the outside atoms. And oxygen gets two bonds, two lone pairs. We're going to pick the oxygen arrangement that has a double bond because it only has one connection. All right. So what we do is we do that. Now we count up the number of dots. 2, 4, 6, 8, 10, 12, 14, 16. So we have 16 dots. We look up here, we have 18. So we need two more. You put the 2 in the center. And you're done. Okay. All right. So this is the bonding structure of sulfur dioxide. And we're going to see, maybe not, but it's a good start. So look at the no valence electrons. Oxygen has the octet 2, 4, 6, 8, 2, 4, 6, 8. But sulfur has 1, 2, 4, 6, 8, 10. Okay. And it can do that because it's found in the third row. So why does the expansion of the octet happen? Okay. And so one of the key things here is that we put the atom with the least electronegativity in the middle of the molecule. So in the last case, you have a sulfur and it has two oxygens attached to it. The way that I kind of think about it is that oxygens are very electron hungry. And what they're doing is basically trying to tear apart sulfur to get electrons. And so what it's going to do is kind of open up sulfur so that sulfur can expand its outer shell into the D, so oxygen can get more electrons. Okay, so that's one reason why you put the least electronegative guy in the middle. So if you look at bonding structures, you usually see there's guys on the outside look like they're kind of attacking the center atom and kind of reaching in to grab electrons. So really there isn't kind of a sharing of electrons. Although it is in the long run, is that the outside atoms are really attacking to try to take care of their desire for electrons. Okay, kind of same thing we talked about in the last PowerPoint. So it's a really dynamic thing. It's just not putting atoms together and putting dashes and dots. Okay, there's a whole dynamic taking place when you do and forming a bond. Okay, I mean there are a lot of classes they talk about just adding dots and dashes and things like that. But if you look at it as a real dynamic thing taking place, it really gives it more life, and that's really what makes chemistry, more alive and more something to look into. Whenever I look at a chemical, let's see a bonding structure, I go, oh, I kind of know what's going on because I look at it, I go center atom, what's going on with that? Okay. All right. So keep that in mind. All right, so one of the things that we just kind of assumed at this point is that you saw single, double, and triple bonds. Okay, and at first glance, you might just think that a double bond is twice as strong as a single bond because there are two of them, and a triple bond might be 3 times. And there's a reason why these single, double, and triple bonds form. And we'll get into a little bit of that in next PowerPoint next week. But what we want to do is look at our single, double, and triple bonds because we're going to find this is not the case. That a double bond is not just 2 single bonds. So what we're going to do is look at the bond overlaps, okay? And that the bond overlaps is where the electrons get shared. One of the reasons covalent bonding stabilizes shared electrons is because the shared space between overlapping orbitals. Okay. Now, technically, orbital, where we put those 2 arrows which represent electrons, is a space where electrons have a chance to be. And we didn't get into that. If you saw the lecture that the Khan Academy had, you would have seen a little bit more about that. But when we talk about electrons, we really don't know where they are. All we do is sort of know where they might be. And an orbital is a high probability of a place to find an electron. But anyways, so when two orbitals overlap from two different atoms, finding that orbital or making that orbital more probable becomes more so, and therefore more stable. So more overlap, the better. So we're going to kind of look at different kinds of overlaps. We're going to look at an overlap called a sigma, we'll call a sigma bond, symbolized by Greek symbol, and a pi bond. And first we'll look at a sigma bond. And we're going to look at hydrogen, okay, H2. So first of all, let's look at the orbital energy diagram. So H2, if you found the bonding structure, just simply H with one bond, H. That's it. There's one shared pair of electrons. The orbital energy diagram for one of the hydrogen atoms is a 1s. This arrow should be inside here. Okay, so it has an s orbital with one electron in it. Okay, remember that s orbitals look like spheres down here. So when they bond, okay, when each hydrogen bond, what they do is their two s orbitals overlap like this. Okay, so let's kind of take a closer look at it. All right, so if you look at the overlap, you would see here's the overlap between the two orbitals of hydrogen. Okay, now there are two things that stabilize this situation. One is the overlap, okay, the shared space where electrons can be. Right, the other thing that stabilizes this is that this overlap is between two sets of protons, which kind of lock these negative electrons into place. So this makes sigma bond very stable, because not only is there a sharing, an overlap, but that overlap is between protons, locking it into place. So a sigma bond is very stable, or stable. Okay, there's other possible sigma bonds as well. You can have s with a p orbital. So here's an s. If you remember what a p orbital, it would kind of look like a figure 8, three-dimensional. But you can get an overlap, okay, between the lobes. Okay, here's the overlap. And notice the overlap is between the two sets of protons. So you can have an sp sigma overlap. And also you can have a pp sigma overlap, right? Where the overlap is between the two protons. Most situations have overlaps, and the overlaps are between the nuclei. So that's what makes up a sigma. You have an overlap that's between nuclei, or between protons. All right, now let's look at the other type called a pi bond. So let's look at a p orbital. Here's your figure 8, or might call it dumbbell, where you might find two electrons. Okay. So, and we saw in the last slide is that they can overlap end to end, and when you do that, you can have a sigma bond. Okay, there's another way that p orbitals can overlap. Okay, they can overlap where the tops and the bottoms overlap. Okay, but the overlap is not directly between the nucleus. In this case, there is an overlap, but it is not internuclear. Therefore, it's less stable because there's no protons really to lock in these electrons. So a pi bond is weaker than a sigma bond. And then also, pi bonds tend to be shorter because you got to get these guys close together. But when you get them close together, that kind of puts these protons close together. And that also destabilizes protons, and they want to repel each other. So that's another reason why pi bonds are more unstable. So they're unstable for two reasons. Both have to do with the protons. One is that the protons aren't locking in the electrons. The other is that they're getting too close and starting to repel each other. So it's fairly easy to break apart this thing we call a pi bond. Right. So let's talk briefly about bond length and bond strength, because we usually just draw the each dash the same length, okay, and we kind of assume this each bond has the same strength. So far, you know, from what we just talked about, we see that sigmas are stronger than pi's. So let's look at bond length for a little bit. Bond length is dependent on what type of orbitals, what we just talked about, SPs are overlap, and also what types of atoms. For instance, comparing two S overlaps or sigma bonds between it. So if you had a sigma bond between two carbons and a sigma bond between two hydrogens, a sigma bond between the hydrogen molecules would be shorter than the sigma bonds between the carbons, and that's because hydrogen is a smaller atom. Okay, this has to do with length. Okay, so a carbon bond is longer, sigma bond, than hydrogen sigma bond. All right, an s orbital with a p orbital forming a sigma bond, like I showed a couple slides ago, where you had S, a circle with the lobe of that figure 8. And that's going to be longer than if you just have two spheres, okay? If you have two P's, if you go back 2 slides, you'll see that the 2P sigmas will have the longest bond because the 2P's are end-to-end further apart. So the shortest of all of these, as long as they're all the same, sigma bonds, these SS orbitals are shorter than SPs, and then PPs are the longest of the sigma bonds. Pi bonds tend to be shorter than sigma. That should be a sigma, not S. All right. Now, in terms of bond strength is dependent on the atom type, okay, and the bond length. So if you have a short length and an atom with strong electronegativity, you got a strong bond. That's as long as it's a sigma bond, okay? So for instance, HF probably has a very strong bond because the fluorine has a very high electronegativity. So that might actually be the case, but so that's what you look for. So even though we draw bonds all the same as single lines, they can be shorter, longer, stronger, or weaker. Okay. Okay. So how does this relate to single, double, and triple bonds? Well, we won't go really into the whys of it. But whenever you see a single bond, one dash, like this case, that's always going to just be one, that's going to be a sigma bond. Whenever you see a double bond, and it doesn't just have to be carbon, but I'm just showing you here carbon. So here's a carbon with a double bond. One of the bonds is going to be sigma, and the other one is pi. It will be a pi bond. And it doesn't matter which one, I just decided to make the red one is pi. A triple bond is going to be one sigma and two pi's. Okay, so the way that the sigmas go is I mean the pi's is that one will be going see these the sigma bond is between the two carbons, while the pi bonds are going to be perpendicular, one going in this direction and one going into the z direction. So not every bond in the molecule is the same, right? So when you see a double bond, it has actually one strong bond and one weaker bond. You have a triple bond, it has one strong bond and two weaker bonds. Okay. Say pi bond stability. Suppose we have two bonds, a sigma and a pi. So here you go. Here's a sigma bond and here's a pi. And a highly electronegative atom comes along like fluorine. What happens? Well, for the sigma bond, the fluorine cannot, that should be cannot, reach and take the shared pair all that well. So it tries to come in and take them, but those electrons are stuck between the two protons and just can't take them. On the other hand, with the pi bond, fluorine comes in, and these guys aren't locked in position. The fluorine can come and take those away. So when you see there should be pi bond, either in a double or triple bond, it can be broken fairly easily. All right, now flip-flop. The two electrons in a pi bond, in a double bond, they can actually move when they are in molecules, especially if they're in a molecule that has high electronegativity. Because they are unstable, they can be pulled away into the valence shell of an atom. And the atom, so that and they can become part of the atom's outer shell. And that can replace the bond. So in a sense, the pi bond becomes a lone pair. And this will happen especially if you have an atom with high electronegativity like oxygen. And so it kind of does it back and forth. So what you get is you get the lone pair will slide up here, and then it'll slide back down. So it'll go back and forth between being a double bond and being a lone pair. Okay. Now, sometimes you won't see that happen very much. You just find a double bond. Other times you'll actually see, you might see more of this, and sometimes you'll see a flip-flop between them. Okay. When you start to see the flip-flop between them, you'll end up with something called resonance structure, which we're going to talk about later. We're going to see the resonance structures really give a lot of stability to the electrons in a pi bond. So this is actually going to turn out to be a favorable thing for stabilizing the electrons of a pi bond. Okay, so let's just make sure we clear up something here. Let's look at a little closer at both the structures that we just put up. So when I draw this, what I have is I have 6 valence electrons of oxygen. So this is the dot structure, 2, 4, 6, 8, and there's 2 that some other atom has loaned to it to share. Okay. Right. Now in this case, what oxygen has done is kind of taken that shared pair over here and actually made it its own. All right. So now, oxygen has kind of said, you know, I'll share one of my electrons with you, but I'm going to take the other 2 and keep them. And it can do that because it has a lot of higher electronegativity and a spot to put the electrons in. Okay, when it does that, it will have one more electron than it usually has. All right. When you count them up. Okay, and so this guy has a negative charge. So whenever you draw a single bonded 3 lone paired oxygen, it technically has 1 negative charge. And that's because one of these electrons was stolen from the atom that's attached to it. Okay. So it has 1 extra electron. So it's O minus. Okay. All right. So what I want to do is I want to give you a pretty important concept in all of this. And it relates to something called charge density. So one of the things about pi bonds is that those, like I said, those electrons in a pi bond are very unstable. And what we'd like to do is have a way to stabilize them. Also, whenever an atom or molecule has a negative charge, if you see that atom or that molecule with a negative charge as a stable molecule, that means that negative charge must be stable on that molecule. Okay, so for instance, if we look at a polyatomic ion like sulfate, SO42 minus. So sulfate has 2 extra electrons. That molecule is very stable. It has 2 extra electrons. Those 2 electrons are very happy on that structure. What makes those 2 electrons very happy? And it's going to relate to charge density. So one way to stabilize the negative charge, and we're going to see the electrons in a pi bond, is to reduce the charge density or the electron charge density on a molecule or an atom. What this means is that spreading the charge out over a large volume. So what you do is it's like taking an electron and spreading it out over the molecule. When this happens, there's no longer a single spot to find a charge, and if it gets spread out enough, the charge virtually is invisible. So if it gets spread out so much, okay, it's still there, but you can't find it because it's spread all out. The spreading out, in a sense, hides the charge from any invaders, high electronegative species. Think of it this way, maybe on an Easter egg hunt. If all the eggs were sitting in the middle of a room, you could easily get to them, but when they get spread out, there's still the same number of eggs, but it's harder to find them, and those eggs are more stable. Okay, they're not going to be eaten. Okay, so this flipping back and forth between double bond and lone pairs is one way to spread out the charge. So the electron, because the electron's moving from bond to lone pairs, so it's moving back and forth. In a sense, it's spreading itself out. Right, there are other ways to reduce charge density as well, and you'll get more into that if you take 122, and it's a really important thing in terms of like acid bases. We will see that a charged molecule, like polyatomic ions, have low charge density and are very stable. Like I said, sulfate is a polyatomic ion. It has a low charge density. It's a big molecule. Okay, it has 4 oxygens and 1 sulfur. So if those 2 electrons get spread out all over that thing, it's almost impossible for somebody that's seeking out the electrons to actually grab a hold of the electron because it's spread out. So the charge can't be taken. The molecule can't interact with atom with the opposite charge because the atom can't see the charge. It moves on. So if Fluorine came by and looked at a sulfate, it might go, I don't see anything because it's spread. I sense there's a negative charge, but I can't find it. All right, and it moves on. All right. Okay. So next thing we want to take a look at something called formal charge, and we're going to be using this. And it's just a short little math calculation, and it's not quantitative in terms of units. It's just a way to help get kind of an idea of how electrons might be shared, how the electrons might be distributed on the atoms in a molecule. We'll be more quantitative about that when we get into polarity in the next PowerPoint next week. So we have this thing called formal charge, just FC, and it's going to equal the number of valence electrons minus the number of dashes minus the number of dots. And what we're going to do is use it to help us figure out, we're going to now see that there's some molecules that can have more than one possible structure, and formal charge will help us figure out which of the structures is most possible. Okay, so let's just go over some formal charges of some molecules and just look at water. So formal charge of, so what I want to do is find the formal charge of each hydrogen in water. So both of these are going to have the same formal charge, so I'm not going to do it twice. So you have number of valence electrons of hydrogen is 1, number of dashes is 1, and it has no dots on it. So it's 1 minus 0 equals 0. So each hydrogen has a formal charge of 0. Okay, the formal charge of oxygen, number of valence electrons is 6, minus the number of dashes, 2, minus the number of dots, 1, 2, 3, 4, and now has a formal charge of 0. One of the things that'll hold true is the sum of the formal charges. So 0 plus 0 plus 0 should equal the charge on the molecule. In this case, this molecule has a 0 charge. So so the sum of the formal charges is equal to the charge on the molecule. That's a check. All right, so let's take a look at formaldehyde. So again, just do one hydrogen for each one. So you have number of valence electrons 1, minus 1 bond, 0. Oxygen, 1 oxygen, so it has 6 valence electrons, 2 dashes, 4 dots, 0. Carbon has 4 valence electrons, 4 valence, minus 4 dashes, 1, 2, 3, 4. And no dots, and so 0. So 0 plus 0 plus 0 is equal to 0. There's no charge on this molecule. So if it would have been like sulfate that has a 2 minus charge, when you add up the formal charges, they would have been minus 2, which should equal 2 minus. All right, so where do we use that, and how do we're going to apply? We're going to combine now our studies of resonance, octet, and formal charge to help us figure out some things about structures. So let's just go back to SO2, sulfur dioxide, and we came up with this structure right here. Well, I saw in a couple slides ago is if you have a double bonded oxygen, you can have that one of those bonds, which is pi, can come out and form a lone pair. So what you can do is you can get other structures. This isn't the only structure you can get. You can get where this guy comes out and has lone pairs out here, and you get this structure. You can have this guy over here come out. Now you got this. Or you can have both of these come out, and then you can have this over here. So actually you have, So it looks like we have 1, 2, 3, 4 possible structures. Okay, now these two structures here, they flip back and forth between each other. Okay, so so they're essentially one structure, and we call this, so this guy is a resonance structure. So if you can get two kind of identical structures with their bonds on different sides, you can have resonance structures. So actually we have 1, 2, 3 different structures here. And what we want to do is figure out which one of these 3 structures is probably sulfur dioxide. So this isn't just simple. It's so you just for a lot of the ones that we went over, like for water, ammonia, formaldehyde, cyanic acid, you won't have that. But a lot of times when you have a double bonds, especially with oxygen, okay, you will have these resonance structures. And I'll let you know when you need to look for resonance structure. So now what we're going to do is try to figure out which one of these 3 structures is probably the best. So we have these 3. Okay, so do they all exist? If so, is there one that's more stable? If not, which one is it there? Okay, and that's what we want to figure out. Which one is the best, or which one is exist? Okay, so what we're going to do is determine the most probable bonding structure. We look at 3 different things to determine what structure is most stable. We're going to look at the formal charge. And structures with little formal charge or not much formal charge are preferred. That's because nature doesn't like to have a lot of unequal stuff. It doesn't like to have plus and minuses all over the place. Just rather have just neutral. Resonance structure. And that's because resonance structure actually increases charge density. So it says reduce, but it means increase. We also say it delocalizes charge. And thirdly, we're going to look at Octet Rule. And there is an actual quantum consideration that suggests that having an octet is better than not. Okay. So in terms of priority, resonance is always going to be preferred. It's going to be our -- priority. Octet is second on the list, and then formal charge. Okay. So resonance is the main thing you look for, then octet, then charge. So what we're going to do is look at these 3 different things for the 3 different structures and try to determine, based on these 3, which of the structures is the most probable. So we're going to take, here's our first structure, and we're going to first find out the formal charge of each atom. So the formal charge of each oxygen is going to be 6, number of valence electrons, minus the 2 bonds, minus the 4 dots, 0. Okay, now the formal charge on the sulfur, it also has a valence of 6, minus 4, 1, 2, 3, 4, minus 2. It also equals 0. So this is pretty good. It doesn't have any formal charge at all. It doesn't have any resonance structure. And in terms of octet, only the oxygen has the octet. So each oxygen has octet, and the sulfur doesn't. So it has 2 octets. All right, second structure. Again, find the formal charge for each oxygen. Okay, so each oxygen has 3 lone pairs on 1 bond. So it's going to be 6 minus 1 minus 6. And when you get that, it has a minus 1. So it has 2 minus 1s on it. And then the sulfur has a plus 2 on it. So a 6 is the valence, minus 2 bonds and 2 lone pairs, plus 2. Okay, just for checking, the 2 plus 2 minus equals 0. So the total charge on this molecule is 0. So, but we have 3 formal charges, which is not a really good thing. There's no valence structure. And again, the oxygens have octet, and a sulfur does it. Okay, let's look at the third structure, which is our resonance structure. Okay, so for each structures, okay, they have 2 oxygens, a double bonded and a single bonded. The double bonded is going to have it's going to have 6 minus 2 minus 4, 0. And it's going to have the charged oxygen is going to have 6 minus 1 minus 6 equals minus 1. And so it has 2 formal charges of -1. Actually, it only has has only 1 formal charge. Okay, so formal charge here. The sulfur, I made a mistake here, has valence of 6 minus 3, not 4, minus 2 should equal +1. So so there's a -1 and +1. So it has 2 formal charges, similar to one we just did. Okay. The last one had 2 minuses and 1 2+. So compared to that, to the formal charges of the second and third, they both had 3 atoms with formal charges. I mean, 2 atoms with formal charges, but in the first case, the charges are bigger, which it counts. All right, but anyways, so 1 formal charge. It actually has 2 formal charges. So it has 2 formal charges. And it has resonance structure, and all the atoms have octets now. So 2, 4, 6, 8. Okay, so let's tabulate that. So formal charge, resonance, octet, and kind of a score from that. So this has no charge. It has no formal charge, 2, and this should be a 2. So these both have 2, but this is more likely to be split because this negative charge gets split out over the whole molecule. Okay. Number 3 structure is the only one with resonance, and it's the only one with 3 octets. Okay, so I would pick the third structure to be my best because of the resonance and structure. It has resonance and it has more octets, even though it has a little bit less formal charge possibilities. Okay, right, so octet and resonance really are key things to determining the right structure. So the real structure of SO2 is more than likely this structure right here. Well, it is. Okay, now let's do carbonate. So we find a base starting structure, count the valence electrons, 4, and then each carbon is 6, so 3 times 6. And it has a 2 minus, so you add 2, so it's 4 plus 3 times 6 plus 2 equals 24. So we need to have 24 dots when we're all done. Here's the skeletal structure. And what we're going to do is we're going to make the oxygens have their number of bonds and lone pairs. 2 bonds and 2 lone pairs. Count them up, and you got 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. Looks good. 24 dots. Done. Oops. Well, something's wrong with this structure. Okay, take a look at the carbon. Carbon has 2, 4, 6, 8, 10, 12 valence electrons. And that's impossible, because carbon cannot expand its octet because it's found in the second row. So this is the wrong structure. So what can we do? Well, because the pi bond can move on the oxygen as a lone pair, we can fix it. All right. So what we can do is we can just move one of these, and it doesn't matter. We're going to move two of the pi bonds as lone pairs, and you end up with this structure right here. Okay. And if you look now, carbon has 2, 4, 6, 8, and each oxygen has 2, 4, 6, 8, 2, 4, 6, 8, and it looks like a good structure. All right. Okay. Well, it turns out that there can be other structures as well, not just this one. Okay, there are two more structures. First of all, the structure we just had, it can have resonance, where the double bond can be here, here, or here. So this structure can have 3 resonance structures. And then you can have another case where all 3 of the double bonds come out. And you get this case right here. Right, what we want to do now is try to see, based on formal charge, resonance, and octet, which one of these 2 structures is the best. So structure number 1, if you count up the formal charge of the oxygens, so that you just pick any of the 3 structures, and they're all going to have the same formal charges. So this would be 6. The double bond is going to have 6 minus 2 minus 4, or 0, and each single bond is going to have 6 minus 1 minus 6. So it's going to have 2 formal charges of a -1. And a formal charge of carbon is going to be 4 minus the 4 dashes equals 0. Now, here's the example. If you sum up the formal charges, so 0, and there's 2 of these, so it's -1 plus -1 plus 0. So the sum of the formal charge is -2, and that's the charge on the molecule, -2. Okay, so this is just a check. Right, so this has 2 formal charges, -1, -1. Now, those formal charges are actually spread out all on the molecule, so it's not really 2 -1s. It's less than those 2 -1s because of the spreading out. It has resonance structure, and if you go back and look at all the atoms, they all have octets. Right, now if you look at the second structure, right, it has all the oxygens have 1 bond and 3 lone pairs. So each one of them has a formal charge of 6 minus 1 minus 6 of -1. So the oxygens have 1 minus 3 times 1 minus, and then the carbon has valence shell 4 valence electrons minus 3 dashes and no lone pair, so it has +1. Again, when you add these all up, -1 -1 -1 +1, it'll be -2, which is the charge on the molecule. All right, so this has 4 formal charges, 3 minuses and 1 plus, and they're not spread out because there's no resonance. And the oxygens have the octet, but the carbon doesn't. It only has 6 valence electrons. So put it in a table. The first structure has 2 formal charges, both coming from the oxygen. It has resonance structure, and it has there should be 3 octets. The second structure, it had 3 formal charges. That should be 3, not 4. It had no resonance structure. Only 2 of the atoms had octets. I don't know why I put 3 here. So this should be a 3 and a 2. And so for sure, the first structure, or the resonance structure, is the way that carbonate is. All right, so resonance structure. Resonance structures are very, very important. What they do is they spread out the charge. They reduce the um, charge density. When it does that, it stabilizes pi bonds. It also stabilizes charge. It makes it hard for other atoms to take the charges or take the electrons. All polyatomic atoms, ions, are resonance structure. This is why they exist. They are stable because of their resonance. And they become particularly stable when you put them in water. And if you go further into chemistry, especially organic chemistry, they'll be talking about resonance quite a bit. All right, oddballs. Sometimes our techniques don't always pan out. In coming up with bonding structure of a molecule, we try to make sense of this without a magic hand waving, such as Octet Rule. We just didn't say, follow the Octet Rule. We try to make sense of it. Put the lower nitrogen negative atom in the middle, okay, and etc. Okay, and I just want to let you know that's just not filling the Octet Rule. There's a whole lot more to it. Okay. But often there are oddballs that I can't explain. Okay. And there's an oddball I'm going to show you now. It's kind of hard to explain. You have to. It takes. You still can explain it, but it really takes some thinking. It's not straightforward. All right. In a lot of chemistry classes, the next problem is just kind of straightforward. But the way that I come up with it, it's not so straightforward. But that's okay. We can end up coming up with the right answer, doing it in a way that I think makes more sense. And that is carbon monoxide, CO. So the first thing we'll do is come up with the starting structure. So we have our skeletal structure. There's no center atom. There's 4 plus 6 is 10. So we need to have 10 valence electrons. Carbon is least electronegative atom. So if you're going to give the two of these atoms, which two of the atoms, their number of bonds and lone pairs, I would pick oxygen because it has a higher electronegativity. Okay. Remember what we did on the other ones is this outer atoms were the higher electronegative, and we gave them their number of bonds and lone pairs. So oxygen should get 2 bonds, 2 lone pairs. Here you go. So now we're going to count the dots. So 2, 4, 6, 8. So we're missing 2. So we just put 2 here. So we got this. Okay. So one of the things we can do is, I said, you can take one of these bonds here and move it outside, and you can get this guy here. Okay. All right. But here's another structure. Okay. Now this is kind of weird. How come you come up with this? Well, there's no reason why you can't. The reason why you can't is because all you have to do is make sure that carbon and oxygen don't have any more than 8 electrons in its outer shell. So instead of taking this guy on the outside, what we're going to do is move one of these guys here. It's a possible structure, so we're going to check it out, see if it works. So far we have this structure here, this structure, and this structure. Well, can we get any more? Yeah. Okay. What we can do is we can move one of those bonds from the triple bond on the outside here over here. Okay. And then what we can do is we can move one of these over here. So you end up with this. So you end up with 5 different possible structures. Okay. Our first one, our second one, our third one, and our last ones. Okay. So what we got to do is go through each one and try to figure out which one is the most probable based on our our checkpoints. So number one, this structure right here, the one we originally came up with. Okay, the oxygen has a formal charge of 0. 6 minus 2 minus 4. Formal charge of carbon is also 0. 4 minus 2 minus 2 is 4. It has no resonance structure and 1 octet on the oxygen. Okay, so this is good structure for octet and also formal charge. Number 2. Okay, formal charge on the oxygen is -1, so it's 6 minus 1, 2, 3, 4, 5, 6, 7, so -1. The formal charge on the carbon is 4, valence electrons 4, -1, -2, +1. So this has 2 formal charges, -1 and +1. Again, there's no resonance structure and 1 octet on the oxygen. So between these two, probably this one is more probable because it has less formal charge. Okay. I think because both have no resonance and they both have 1 octet. Okay, number 3. It has a +1 on the oxygen. So 6 minus 3 minus 2 equals +1. Okay, and then carbon is 4 minus 3 minus 2 equals -1. It has no resonance structure and it has 2 octets. Okay, now this structure here, in terms of, is the best in terms of octet. So now let's look in terms of the formal charge. Seems to have the same kind of formal charge as these has 2 formal charges. So if you were to look at formal charge, it looks like this one would be the best. How about the difference between the formal charges of these two here? They both have a 2 formal charges. It turns out that this guy up here would be more likely than this one down here. And that's because you want to have the negative formal charge on the most electronegative atom. Okay, so here the negative is on the oxygen, which is more. So in this case, it puts the negative formal charge in carbon, which kind of doesn't make a whole lot of sense. It's kind of saying that carbon has a better strong pull on electrons than oxygen. So this structure ends up being kind of weird. All right, there's no resonance structure, but it has 2 octets. So let's move on. So of these 3, this one looks the best formal charge, but this guy here looks the best of resonance structure. Okay. Again, I told you resonance structures probably has a stronger outcome than anything else. Outcome, octet, and resonance structure. Okay, our 4th structure. Okay, this says the oxygen has +2 and the carbon has -1. This is really not good. Okay, it's not good for a couple reasons. One, there's large formal charges. Okay, and also putting a +2 on oxygen, that's really hard. Okay, oxygen doesn't like to give up negative. So this guy I really is not favored at all. This is probably the least favored of all of them because of this. And it has 1 octet. Okay, and that's with the carbon. And the 5th one, it's kind of like the triple bond is that it has the oxygen on the +1, -1. It has no octet. So when it comes down to it, which ones are our best? Okay, so let's go through them all. For the first one, had no formal charge. So if it all came down to formal charge, I would pick this guy right here, number one. All the rest of them all had, both atoms had formal charge. Okay, now number 4 is probably the worst one, so I'd probably kick that one out as our least acceptable. All right. In terms of octets, none of them have resonance structure. In terms of octet, well, her third structure had 2. Okay. All right. Okay. And what happened is the octet is going to outweigh any of this here. Okay. So the 2 octets outweigh any of it here. So number 1 is because of formal charge, the other 4 are formal charge, so forth. But number 4 is probably the best because it has 2 octets. Right, and in the long run, you just have to remember that bonding doesn't have to be strict, and sometimes you have to really think about it. You just can't pop, plug, and chug. You come up with an answer. Have to make sense.